Hello, my name is Jaden Calberter. I am an EE for Group 4, also known as Bright Descent. Our project is called the Gravity Lamp, and I'm responsible for the power generation and storage and the lighting subsystems. Seen here is the interface block diagram our team created and shows how everything is connected and interfaces together. I am responsible for the block seen in purple. To the left of the diagram in purple is the power generation and storage subsystem. The purpose of the power generation and storage subsystem is to ensure that our battery is being sufficiently charged and is supplying sufficient amperage and voltage to power the rest of our electrical components. The load/charge controller is the central component of this subsystem, handling the power input from the generator, which is connected to the gear train, and the power input from the wall, which is connected to an AC to DC step-down component. Both of the power inputs are then fed to the battery. As for the lighting subsystem, seen to the right, its purpose is to provide at least 400 lumens to meet our project specifications. Just before the light, there will be a DC to DC voltage regulator. For testing the power generation and storage subsystem, I started by setting up the buck boost converter, which takes input from the charging block and steps up the input voltage to 12 volts. The load/charge controller is rated for 12 volts or less, so having the maximum input voltage flowing into the controller will reduce charging time when the system is being charged by wall power. After setting up the buck boost converter, I took an initial measurement of the charge in the battery before proceeding with charging the battery from the wall. During the charging process on the load/charge controller, you can see a red light turn on. This indicates to the user that the battery is actively receiving charge from the input. I then measured the battery after charging it for 5 minutes off the wall power. Before proceeding with charging the battery with the generator, I initially connected the generator and battery to the charge/load controller. Unexpectedly, the generator started spinning like a motor due to the back current caused by the battery. To solve this issue, I installed a diode in series with the positive line from the generator to the charge/load controller. To charge the battery with the generator, I used a drill to spin the generator as close as I could to a constant 800 RPM to simulate the RPM input we are seeking from the gearbox. Just as I did when testing the power generation and storage subsystem with the wall power as an input, I measured the battery's charge before and after charging the battery for 1 minute. For the lighting subsystem, I wired the LEDs in parallel with each other so that they all had the same brightness when the system is turned on. Each LED was then wired in series with a resistor as a means of controlling the current flowing into it. When it came to testing the lighting subsystem, I powered the system by connecting the battery to the charge/load controller, and then connecting the lighting subsystem circuit to the load output terminal on the charge/load controller. Once powered on, the light produced by the system was visually observed. From visual observations alone, it appears that the lighting subsystem in its current configuration produces enough light to fulfill our project specifications. In conclusion, our testing successfully validated both the power generation and storage subsystem and the lighting subsystem. By integrating a buck boost converter, we maximize wall charging efficiency at a stable 12 volts. We also identified and resolved a critical back current issue by installing a series diode, preventing the generator from motoring. When spinning the generator at our target 800 RPM, the system demonstrated reliable power capture. Finally, our parallel LED configuration functioned perfectly, providing uniform brightness that visually meets our 400 lumen specification. With the core power management and lighting circuits verified, our next steps will focus on long-term efficiency testing and full integration with the mechanical gear train, housing, and electrical subsystems. along with improving testing methods to make the acquired observations less subjective.